I have a joint position, so between Imperial College London in the UK and Yonsei University in Korea. But I spend most of my time in London. But originally, I guess my training started in Ireland. So I'm originally from Dublin, and I studied at Trinity College, which is a university right at the center of Dublin, which is the capital of Ireland. And actually, I think there are several things in common between Ireland and Russia. So we have many famous writers, and I'd say also a love for alcohol. And so some of the graduates from Trinity College include Samuel Beckett, the playwright, Bram Stoker, who wrote Dracula, so he wrote that in Dublin, Jonathan Swift, who wrote Gulliver's Travels, Oscar Wilde, playwright, and then William Hamilton, who is the mathematician who, I guess, he developed Hamiltonian mechanics, which was later used then as a basis for quantum mechanics. So that's where I started, and where I've ended up is in London. So I'm based at Imperial College, which is in South Kensington, so a very nice part of London. And I'm part of the Royal School of Mines. So this was an institution established in the 1850s, which was a government research lab. So it focused on the study of minerals and metals. And it then later became part of Imperial College, but the Department of Materials is based in this building. And my office, although I haven't been there in 5 weeks now, is up on the 3rd floor. So Imperial College is quite strong in physics and material science. So several Nobel laureates in diffraction and astrophysics and holography. So originally I was trained in computational chemistry and physics for my undergraduate degree. And I guess for my research career, I focused on the theory and simulations of crystals in particular. And generally what we're interested in is excitations of crystals. So it could be electronic excitation, so looking at redox processes to chemists, and vibrational excitation, so looking at phonons and phase transitions, and looking at optical properties, and a lot of our work is focused on defects in crystals. And then recently trying to figure out how we can use data and statistical techniques to accelerate sort of materials exploration and discovery. And the inspiration for the seminar I'm giving today was actually from a series of perspectives published in Nature Chemistry towards the end of last year. And they were focused on, they asked 50 chemists where they saw chemistry evolving over the next decade. And they asked several computational chemists, and interestingly enough, each scientist gave a similar perspective. And that's that the field of computational chemistry and computational material science has really been changing over the past 5 years and continues to change. So I decided to put together a seminar that would hopefully get across some of those changes to more general researchers in chemistry and material science. So hopefully I succeed today in getting across some of the excitement. So starting point, in terms of just the definition of what is computational chemistry. So looking at the end of computational material science focused with, I guess, atomic interactions. So this is the current definition from IUPAC. And it's using mathematical methods for the calculation of chemical properties or for the simulation of molecular materials behavior. And it also includes synthesis planning, database searching, and combinatorial library manipulation. So it's quite a wide sort of perspective on what is computational chemistry. So it's using computers to do many different types of chemistry. So it's not just running DFT calculations, for example. And it's a discipline that has been changing over the decades. So along with the hardware we've had available. So I really like this photograph from the 1950s of a 5 megabyte hard drive, which had just been developed by IBM, being loaded onto a truck. And of course, today we take a picture with our phones, and that requires more than 5 megabytes of data storage. So you'd have a single photograph stored on this crate. And this year just saw the emergence of the first commercial quantum computer. So again, from IBM, the IBM Q system, And it's just curious that it has similar dimensions to that old hard drive. And so you could think, actually, where in 10 or 20 years, where is quantum computing going to be? Is it going to be miniaturized to the same extent that we've seen sort of solid state data storage? Okay. So today, the seminar has sort of 3 segments, hopefully not too long. So first, getting everybody onto the same page in terms of computational material science and describing interacting atoms. Then I'll give just a topical example from my research, trying to push conventional methods, looking at organic-inorganic systems. And then the final segment is looking at how things are evolving with the use of data and statistics. Okay. So the starting point, I guess, for using computers to model how elements from the periodic table interact is treating them as classical objects. So you could think about having atoms sort of connected by a spring, and then what you need to determine are the spring constants. And generally we refer to this as molecular mechanics. So the application of classical Newtonian mechanics to model chemical interactions and chemical systems. And this is typically done using analytic functions. So as undergraduates, usually you come across, probably the first time you think about interatomic potentials would be a Lennard-Jones interaction. So here we have what we refer to as a 612 potential. So in the 1920s, John Lennard-Jones was thinking about the interaction of noble gases with the surface of a solid. And you think about having a gas far away, so there's no interaction, and you bring it closer to the surface and you get some favorable interaction. But if you bring it too close, it starts to become repulsive. And so this interaction potential describes the attractive regime as well as the repulsive regime. And I guess there are some branches of statistical physics where people can spend their whole career looking at the properties of sort of hypothetical Lennard-Jones solids. So thinking about spheres interacting with these pairwise potentials, and you can get the emergence of some very complex behavior. But generally, if you want to describe sort of real materials, so perovskites, spinels, you have to move to more complex functional forms. And many functional forms have been developed. So there's an array of 2-body potentials, 3-body potentials, 4-body potentials that describe different materials in different conditions. So there's many implementations of molecular mechanics, quite general, but usually when you go to more complex functional forms, you have more parameters. So it's more difficult to fit that functional form for a particular material. And so you have the problem of parameter fitting, and that you have too much, generally you need a lot of known data in order to fit a reasonable molecular mechanical model for a complex material. But nonetheless, you can still extract very interesting physics and material science. And the big advantage of molecular mechanics is that you can run simulations of systems exceeding 1 billion atoms, is now the state of the art. So you can simulate protein folding, radiation damage, crystal nucleation and growth, and sort of large-scale diffusion events. And this is just one example from the recent literature. So taking a simulation cell that's a very large box of liquid iron, then you cool the liquid and it crystallizes, and then you see the natural emergence of microstructure. So you see grains, you see grain boundaries, you see dislocations that are naturally forming. And this is from a very simple pairwise interatomic potential. And it just shows you that very local chemical interactions can give rise to very complex emergent behavior, so the microstructure. So none of this was programmed into the sort of the pairwise force fields, but it emerges due to the collective interactions. And molecular mechanics is still developing. And one of the bigger developments recently has come from Google. So they released a new classical molecular dynamics package. Now, why this seems to be quite special, so in the past, computational chemists would typically program using C and Fortran. So programming languages that are quite explicit and run quite quickly on large-scale computing systems. But this is one of the first examples of a pure Python code that's sufficiently fast that you can do real simulations. So it's taking advantage of a feature of Python called automatic differentiation. So it's a way to differentiate Python functions very quickly. So I think that's a new stream of research that's emerging from molecular mechanics. But as a chemist and for many branches of physics, generally you don't care about classical interactions, you care about electrons and materials. So you want to understand chemical bonding and the response of electrons to different perturbations. So you have to move from classical mechanics to quantum mechanics. And so you're moving often from analytic equations and solutions to numerical methods. And generally what we're interested in is solving the Schrödinger equation if you have light elements in the periodic table, or some approximation to the Dirac equation if you care about relativistic effects. So if you have a lead-based semiconductor, then you typically have to include spin-orbit coupling, which emerges from the Dirac equation to give you a quantitative description of the system. So usually what we need to do is construct a Hamiltonian for our system, and the type of Hamiltonian really depends on the properties that you're interested in. And often the equations look quite simple, but due to the many-body nature, if you're dealing with any system with more than one electron, they become difficult, if not impossible, to solve exactly. So we have to introduce approximations and use computers to come up with numerical solutions. But to cut a long story short, I think in material science, the workhorse method is actually DFT, or density functional theory. So the majority of computational material science right now uses DFT, which really, to simplify things, is a remapping of many-body quantum mechanics. So instead of worrying about individual electron-electron interactions, we just remap the problem into a real space, three-dimensional electron density. So practically, DFT calculations of materials are lower cost, so they've been quite widely applied. And of course, the Nobel Prize was awarded, I can't remember when. I think it was around the start of my undergraduate. So it must have been, I can't remember. But there was a Nobel Prize for DFT awarded to Walter Kohn, who was at Santa Barbara for many years. So I would say two disadvantages of density functional theory and related methods. So one is their computational cost. So typically we have to use very large computers to do meaningful calculations. And this relates to an order n-cubed scaling problem that's related to the underlying matrix diagonalization. So what that means, if you want to describe a system that's 10 times more complex, so 10 times more atoms in a unit cell, the cost of solving the DFT equations increases by a factor of 1,000. And this is really just due to the fact that we have to get eigenvectors and eigenvalues, and those underlying algorithms scale order n cubed. There's many groups working on linear scaling methods, so taking advantage of sparse algebra, so when you have very large systems, but generally they're not really at large scale production level yet. So practically many of us researchers are stuck with this order n cubed. So although computers are getting bigger, in terms of what we can solve with DFT is sort of remaining approximately the same over time. But that's changing and people are starting to integrate new methods. So again, actually more work, a collaboration between Google and the Department of Physics at Imperial College, combining many-body quantum mechanics with some advances in deep neural networks. So trying to use sampling to help ease the cost of accurate quantum mechanics applied to molecules and materials. I think the second problem with quantum mechanics sometimes is recovering chemical concepts. So in chemistry and material science, often we learn sort of intuitive rules for chemical bonding. So ionic bonds, covalent bonds, electron counting, crystal field splitting. And sometimes it can be difficult to extract those concepts back from quantum mechanics. So what we end up calculating relies on delocalized electron density and wave functions. And if we want to extract intuitive concepts, usually we need to project those wave functions onto local atomic centers. And there's many different ways to do it. And then there ends up being many fights in the literature. For example, if a bond is covalent or if a bond is ionic, because it depends on how you partition the electron density. And so I've been involved in several of those fights. So you see many papers published saying, oh, this well-established rule fails when you run a quantum mechanical calculation. But sometimes people overinterpret the quantum mechanical results. That you just need to be careful, so relating reality with what you can actually predict on a computer. In terms of how the field is evolving, one big change over the past 10 years is there's a big move towards open source. So making packages and tools openly available. And I think now the barrier for entering this field is really been decreasing. So if you're interested, you can download Abinit, for example. It's a freely available DFT package. If you have a fast laptop, you can install it on your laptop and run some simple calculations. And there are other packages like ASC, the Atomic Simulation Environment, which is a Python infrastructure that enables you to set up and analyze results based on many different DFT packages. So it's a really exciting time for students to start to use or start to run their own DFT. And just to give you an idea of what can be useful for material science, so what can DFT calculate that's useful? So a wide range of properties. So you can think about structural properties, so comparing to diffraction experiments, vibrational related to infrared and Raman spectroscopy, thermodynamic, so comparing to calorimetry, or whether a particular reaction happens or not. Thinking about defects, so defect concentrations, defect diffusion, comparable experiments, and then thinking, really pushing DFT to its limit in terms of the length scales we can simulate. So thinking about surfaces, thinking about grain boundaries, and comparing again to comparable measurements. So I think increasingly as experiments are becoming more accurate, so going to shorter length scales, and DFT-like methods are becoming more affordable and moving to longer length scales, recently there's a convergence between what we can simulate and what can actually be measured in the lab. Okay, so that was just my sort of setting the scene and hopefully getting everybody onto the same page. So in this section, I wanted to, I guess, introduce a bit closer to my research area, so thinking about hybrid materials. So in terms of my background, really, as an undergraduate, I specialized more in chemistry. And then in terms of my PhD and postdoctoral research, I moved more towards semiconductor physics. And then I was really excited using metal organic frameworks as a base of combining those two areas. So having materials that have organic and inorganic components, and that can be conductive. And this is a really nice map from Tony Cheetham from quite a while ago on the different types of hybrid frameworks that can be formed. So thinking about the dimension of inorganic connectivity and the dimension of this type of inorganic, organic, inorganic connectivity. So a material like methyl ammonium lead iodide used in perovskite solar cells, and I saw you're going to have talks over the next couple of weeks, they would fall in this top corner here. So there are materials where you have a three-dimensional connectivity of inorganic nature, so a lead iodide framework that contains molecular components. So you have zero-dimensional organic units. So you have a molecule that's present inside a repeating crystal. So many of the hybrid perovskites would fall in this top corner. Many chemists would think about metal organic frameworks as being down here. So you have three dimensions of this type of connectivity. But there are two extremes, and you can have mixtures, you can have layers, you can have rods, different types of materials that can be formed. And I think there have been published examples of each of these classes. But if you Googled metal organic framework or MOF, you'd probably get something like this. So these are what most chemists would think of. So porous solids that have organic and inorganic components. And in this case, these spheres represent pores inside the crystal. So usually these are low density solids. And a lot of the first generation of research has focused on gas storage, gas separation, and some sort of passive catalysis. So the fact that you have very large internal surface areas, you can then store large amounts of hydrogen or CO2 inside these crystals. But that's not what got me interested. I was interested more in physical responses. So at the time when I got interested, there was this paper in Science, so reporting colossal thermal expansion in a cyanide framework. So this particular material, due to its topology, when you heat it, you get a large contraction along one crystallographic direction and expansion along another. And when you work out the thermal expansion coefficients, they're really giant. So you get giant expansion and contraction at the same time. Again, related to topology, some of these materials have open and closed forms. So this particular framework, DUT49, with a very mild stimulus, the material can transition from being porous to non-porous. And when you look very closely, there's actually only very small changes in bond lengths. What's really changing between the two forms are the bond angles, so between these structural units. So you're getting these phase transitions that are very low energy, so a very mild stimulus can trigger between an open and closed form. But then what really caught my attention was some work on amphidynamic materials. So these are defined as crystals that have collective motions of molecules inside them. And so you end up getting a hybrid of what you'd expect between the dielectric behavior of a regular crystal and the dielectric behavior of a liquid. So you can get really interesting order-disorder transitions depending whether these molecular components inside a crystal are aligned or anti-aligned or completely uncorrelated. And so this inspired a lot of my early work on hybrid perovskites, because there's a clear analogy between these systems and methylammonium or formamidinium lead iodide. So thinking about dielectric effects. And another interesting point, so there's a Nobel Prize in Chemistry 4 years ago for molecular machines, so related to Fraser Stoddart and his collaborators. But a lot of their research now is moving from sort of isolated molecular interactions to trying to have correlated molecular behavior in crystals. So there's a convergence between many supramolecular chemists are now moving into the molecular organic framework area. So trying to take advantage of having ordered arrays of molecules that can interact inside a crystal. So I think this is a really exciting area of research. In terms of simulations, there are many challenges, both for molecular and quantum, sort of molecular mechanics and quantum mechanics, due to the fact that the unit cells usually are very large, the complex structures. Often the structural chemistry is quite poor because there's lots of hydrogen, and hydrogen is very difficult to resolve from X-ray diffraction. Also, the materials tend to be quite soft, so you have dynamic behavior and very large range for vibrations. And what's made things a little bit easy for running simulations is that there have been some very kind people developing databases of computational ready structures. So trying to take experimental structures, removing disorder, putting in the hydrogens in reasonable places. So there's this data set of 14,000 structures that you can download and then run your own calculations, or even use them to try to refine diffraction data, for example. But my research has been mostly focused on trying to have conductive materials and trying to figure out how we can increase electronic communication between the organic and the inorganic building blocks. So playing around with different factors, playing around with linkers, metals, ligands, different oxidation states, and trying to sort of increase the transfer integrals between different building blocks. And again, to cut a long story short, there's been a lot of progress in this area, many exciting experiments and high performance conductive materials, in particular from the group of Richard Dinka at MIT. So the different classes of high mobility, of low mobility, of where electrons transport through bonds and where they transport through space. So if you have, I guess, pi stacking of ligands, that there seems to be transport through the oriented ligands. So where a lot of our research is at the moment is, again, with compositional engineering, so playing with metals, playing with ligands, but now playing with guests, so thinking about introducing electroactive species into pores, so you can have different band alignments, but also thinking about epitaxial strain. So it's now possible to make thin films of these metal organic frameworks. Because they're soft, you can have very large strain compared to traditional inorganic materials. And strain can play with the electronic structure. So it's a big area of research. On the applied side, there's the first reports of MOF batteries, integrating them into solar cells, supercapacitors, and even the first MOF superconductors, so at very, very low temperatures. So I think below 1 Kelvin. So not very exciting, but it shows the potential. Okay, so that was just a quick, I guess, snapshot of my research. So just in the last 10 minutes, I will move on to data and statistics. So what's getting people excited here is a possible paradigm shift in science. So thinking about how science, I guess, started as an empirical activity. So you'd perform an experiment and you'd generate some data. And then there was an era of very powerful theory-driven science. So theories of thermodynamics, of electromagnetism, of quantum mechanics. And then we had the addition of computational science. So using digital computers to solve equations that weren't possible to solve by hand. And now we have a new toolkit, which could be using statistics and data-driven science. And the question is, have we entered this new paradigm yet? That's a big question. So one of the motivating factors is that integrating simulations and statistics could decrease commercialization times. So if you look at the past, usually it takes 2 or 3 decades between when you discover a new material and when you have a commercial device. And there's been various analysis. So this is actually reading a nice paper led by Tonya Bunasisi, based at MIT, and predicting that we could have a 10% or more factor, not 10%, a 10-fold increase in the, or decrease in the time that it takes. So going from 20 years to 2 years between identifying a material, sort of optimizing its performance and developing device technology, and then realizing a product. And there's a really nice discussion of where theory and simulation can feed into each of those factors. And I think machine learning is, in terms of work at MIT in Singapore, is really feeding into this automated feedback loop. But what I wanted to introduce is thinking more of the chemistry, so where machine learning is starting to play a role. So my definition is simply where we're using statistical algorithms that learn from some training data and build a model to make predictions. So some of the applications we're seeing using machine learning to develop sort of faster computational tools. So avoiding some complex equations, we can train a model and then it becomes very cheap to make predictions. Trying to learn from existing data. So there's a lot of work on text mining. So trying to extract information from published papers and generating a database and learning from that. So far, a lot of the data mining is based on the English literature. So of course, there's a lot of hidden Russian literature that could be tapped as well. And then other groups are using machine learning sort of directly, where you can have computer-controlled synthesis and characterization. Then you could have a machine learning optimization workflow, for example. But machine learning is very broad, and there are many different classes of models that you could think about using in training. So many of us already would be using a regression. So think about, you have data, you want to fit a model. So the many regression tools for sort of simple model fitting. In terms of classification, there've been some nice examples in the literature of using machine learning to predict reaction outcomes. So if you mix together different reagents under different conditions, what's the outcome going to be? And there's examples of clustering being successful, in particular for high throughput crystallography and tomography, where you generate very large data sets and you want to identify quite quickly interesting subsets of that data. So clustering can be useful for that. And in terms of materials design and molecular design, reinforcement learning is emerging as quite a popular tool. So you have a particular target in mind, and you want to sort of modify your molecule or material to maximize your score towards that target. So it could be the yield for synthesis. It could be trying to find a material for LEDs, so high radiative efficiency, for example. And I think there's a really nice Russian blog on the basics of machine learning that you can follow. If you're bored at home, so some of my colleagues at Imperial College, so Sam Cooper, being one of them, have developed an online course for teaching the mathematics underlying machine learning. And it's quite amazing. They've had over 100,000 people complete their course. So it's free to, I think it's free, to sign up on Coursera. So you can sign up on the course and then you follow a series of online lectures and you get some activities as well to try to teach you the more fundamental side of machine learning. So some of the more core concepts. What I would say is that not everybody is on board. So there's a big, I guess, section of the community in material science and in chemistry and physics that are skeptical. And I really like this cartoon. So it's sort of a parody of machine learning where you have data, it feeds into some pile of linear algebra, and then you have some prediction. And all that you need to do is stir the pile. So play around with your feature set, play around with your hyperparameters until the answers start to look reasonable. And so one of the big questions when you go to conferences now is where's the new insights? So where's the new knowledge that you've actually gained from your machine learning? So there's no point just fitting a black box model, that you actually want to learn something from the data. So I think the field is sort of evolving right now in terms of saying how we should use machine learning tools and what they can be useful for, and also how we think about reporting them when we present talks and publish papers. But on the positive side, I think we have many available tools that make research very exciting right now. And in terms of our undergraduate curriculum in our materials department, so we've recently switched where students used to learn MATLAB. And now in first year, they learn Python. So that started 2 years ago. In second year, they start to use Pandas, so a library for dealing with large data structures. And the idea is by the time they get to their final year, they'll be doing the research projects using electronic lab books, so Jupyter notebooks, where they'll have all their data processing. For machine learning, so there's a range of packages like scikit-learn and TensorFlow that allow you very quickly to train models. And then if you want to play around with plotting data, there's Matplotlib has all the basics, and Bokeh and Plotly are a way to deal with multi-dimensional data sets. So if you want to try to look at different correlations, you can very quickly do it using some freely available packages. And even more specifically, when you look at any particular research area, there are often many tools available. So if you work on crystallography, of course, you spend a long time learning about different symmetry elements, learning how to use crystallographic tables. But these days you can sort of pip install spglib, which is a Python library, contains all symmetry elements. You can very quickly load this library, open a crystal structure, identify symmetry elements and manipulate them. So this is just showing how things are changing. There's, I think, people that are specialists in each discipline putting together very useful libraries that decrease the timeline for doing interesting science. So it's all about making research faster and more reproducible. And so along with those tools, we have to think about how we make our data available. So there's a big movement for open data. So when we publish papers, making that raw data available so people can reproduce our results, so they can reuse it for different types of studies, and to enable machine learning. So what machine learning really needs is lots of data. So quantity, quality, and diversity. And that's something that's limiting applications in material science. Crystallographers have been in the lead because they have very big databases. Starting from the 1960s, so the Cambridge Structural Database has over 1 million entries. And they also have a format that's human and machine readable. So the CIF file is not very elegant, but you can open it in a text editor and understand the information, understand sort of, you also have metadata saying usually what temperature, what machine was used to generate that diffraction data. And what we're seeing now is people building data sets in different application areas. So this is one example from UCSB on thermoelectrics. So you can go to their website. I didn't put the link. So it's linked from the website of Ram Sheshadri, who's a professor at UCSB. I guess you can Google this and you'll find it. And you can play around based on published data from the literature. You can plot resistivity versus Seebeck coefficient versus something else. Look at different correlations and then look at each of these points as a particular material. So you can download the raw data. And we're seeing similar things for batteries. So this is a published paper, a published sort of data set on batteries. So again, you can have some fun. Okay. So I think I will skip ahead because I've been talking a little bit too much. Maybe just to say where we've been using machine learning is, or I guess what gets me sort of excited using these tools is thinking about exploring the space for new materials. So thinking that known materials, so what's in current databases, what occurs naturally, is only a small fraction of what's possible. And we cannot explore all of that space using conventional methods, but using sampling-based approaches, it starts to become possible. So that's where we've been doing a lot of research and developing some tools in that direction. But I think I will skip to sort of the conclusions. And so what I tried to get across in this seminar is that there are many exciting developments in materials modeling. So we're moving sort of analytical tools at the start of the 20th century that are still being used now, but they sort of try to idealize chemical interactions, to an era of numerical methods where we had sort of numerical integration and solving partial differential equations, to a case where we have new statistical tools. And so we can start to combine these methods in interesting ways, but generally we're limited by available data. So we have lots of available structures of materials, but there's very few systematic data sets reporting interesting properties. And that really limits of what we can, in terms of what we can do. Thanks to my research group and funding bodies, and thank you all for your attention. So I think later I'll put the slides for this lecture up on this link. So yes, thanks.